Welcome back to our Chem 152 video series. In this video, we'll show you how to find activation energy and frequency factor for a reaction. This question says that a certain reaction has a rate constant of 2e-8 at 300 Kelvin, and the rate constant changes to 8e-8 at 310 Kelvin, and we are asked to find the activation energy. The equation we use goes like this. We'll say R times Ln of K2 divided by K1 equals activation energy times 1 over T1 minus 1 over T2. Let's start from the left and work our way to the right, and we'll talk about each of these letters. R is going to be the gas constant. For the gas constant, you may use 8.314 joules, or you may also use 8.314 e⁻³ kilojoules, depending on what units you would like to use for the activation energy. K2 and K1 are going to be rate constants. Notice that these are not uppercase K's, but lowercase k's. The fact that they're lowercase tells you that they are both rate constants, not equilibrium constants. EA stands for activation energy. T1 and T2 are the temperatures. Note that any temperature you use in this equation must be in Kelvin. Now that we've listed out the meaning of each letter, let's see which ones we know. We are given two rate constants in this question. We have 2e⁻8 and 8e⁻8, meaning that we know both rate constants. We do not know the activation energy. That's our goal for this question. We'll box that in, and we'll put a question mark next to it. We also know the temperatures. Temperature 1 is 300 Kelvin, and temperature 2 is 310 Kelvin, meaning we know both temperatures. We can select whichever gas constant is more convenient for us. If you want to use kilojoules in your answer, we'll say 8.314 e⁻³ and check that off as well. If we plug all the numbers in, here's what we'll have. 8.314 e⁻³ multiplied by Ln of K2 over K1, so that's 8e⁻8 divided by 2e⁻8. That'll give us the left side, and then we'll say that's equal to activation energy, which is unknown, times 1 over T1, which was 1 over 300, minus 1 over T2 is 1 over 310. To make the algebra easier on yourself, I recommend that you go to the left side and collapse all of this math down to a single number. We can do that in a calculator. We end up with 0.0115 on the left. We'll say this equals EA times these fractions. We can go to a calculator and enter these fractions. We'll end up with 0.0001075. Then we'll divide both sides by the number that is next to the activation energy. When we do the math, we'll end up with an activation energy of 106.95 kilojoules. This is the amount of energy it takes to get over the energy barrier and start the reaction. We can use this activation energy to help us find the frequency factor. The equation we use to find the frequency factor will be Ln of A equals Ln of K plus activation energy over R times T in its own set of parentheses. The A is the frequency factor, and that's the objective of this question. We'll place a box around that to remind us of that. The lowercase k is the rate constant, and we can use either one we want as long as we stay consistent. We'll use rate constant number 1 here, but in reality it doesn't matter too much which one you use. EA is of course the activation energy, which we know. R is once again the gas constant, and T is still the temperature. To stay consistent, we'll use temperature number 1. We know that our first rate constant is 2e⁻8. Check that off, that's the K. The activation energy was 106.95 kilojoules. We'll check that off. The gas constant is 8.314 times 10 to the negative third kilojoules. Make sure that matches your activation energy. They must both use kilojoules or both joules. As long as they match, it's okay. We'll check that off. Temperature number 1 was 300 Kelvin. Check that off as well. Now we know everything on the right side, and now we can set the equation up by saying ln of A equals ln of 2e negative 8 plus activation energy, 106.95, divided by parentheses, the R, 8.314 e negative third, times temperature, 300. Since we know everything on the right, we can collapse that down to a single number. We can go to a calculator to do that. We'll end up with ln A equals 25.15. Now, in order to solve for A, we will take a base e exponential. So if we take the base e exponential on both sides, we'll get A is equal to lowercase e raised to 25.15. If we perform this in a calculator, we will get 8.38 times 10 to the 10th power. Don't be too surprised if you get very, very large answers for your frequency factor. And so this is how we find both activation energy and frequency factor. Thank you for watching, and we'll see you again soon.